Alrighty guys, today is our last day working with dihybrid crosses and it went awfully quick if you ask me. It was only about 3 days that we did them. So I wanted to give you some more challenging problems. It asks some more detailed questions. So you guys already know how to go through and set up the cross. You're going to be working them out longhand for the most part here, but there's not very many. For question number 2, you're going to be using all the information that you have in your cross in order to answer those questions. Now when it says possible genotypes here, it wants you to say all of the potential genotypes for producing a tall plant with purple flowers. And you can see what letters you should be using over here. So give me all the possibilities that you could be given. And it asks that for each one of these questions. Give me all the potential genotypes. And for some genotypes, you might only have one option. So just make sure you include everything. Questions 3 and 4 are very much the same as questions 1 and 2. You work out the Punnett square, it gives you the cross, and you answer the questions here on the side. Question 5, you're just setting up a Punnett square along with question number 7. If you want to try to do it the shortcut way, you can. And here we have questions 6 and 8 are going along with questions 5 and 7, just the same as questions 1 and 2 did, and you're giving possible genotypes. I scrolled through all these because I wanted to kind of help you out with these ones down here a little bit. They're different in that you don't actually have to work out any Punnett squares per se, just kind of information that they're expecting you to almost be able to do in your head, but you can definitely show a little bit of work off to the side. So I'm going to do a couple of these with you, and then I'm going to let you guys finish them up here. So number 9 says a tall pea plant with terminal flowers, which is flowers on the ends of the stems, is crossed with a short plant that has axial flowers. All 72 offspring are tall with axial flowers. This is a dihybrid cross with the height and flower position traits showing independent assortment, which means that they are not linked at all. Name the dominant and recessive alleles. We don't have a textbook, so you can ignore this part here about using textbook page 262. So the dominant and recessive alleles. So we had a tall pea plant with terminal flowers. All the offspring are tall. So if all of them are tall, tall is going to be dominant. So short is going to be recessive. And they all had axial flowers. So axial is also going to be a dominant trait, and terminal would be the recessive trait. I know this because the plants are completely opposite that they crossed. We had a tall pea plant with terminal flowers, and we had a short pea plant with axial flowers. So we had all 4 traits being shown to us, and whenever it came out of it, all of the offspring were tall with those axial flowers. So that's why tall and axial have to be dominant. Give the genotypes of the parents and offspring in this cross. So if it's telling us that all of the kids were tall with axial flowers, but we had the parents were varying, the parents would have had to have been true breeding for this. Otherwise, our children, we would have had a mix of their traits, meaning that they would have been more than just tall and axial. Maybe we would have had a short one in there, maybe we would have had a terminal flower in there, but we didn't. So that means that our parents had to be completely true bred for their traits. So tall with terminal traits. I'm going to do lowercase t's, capital A's. So that's my parents. My children were all hybrids. Predict the F2 offspring when the tall axial F1s are allowed to self-pollinate. So that means whenever I would do a cross, I'm going to be crossing this here. 2 that are heterozygous will cross together. Whenever you cross 2 heterozygotes, you're going to show every single trait that you can. So you'll have 4 different traits. The ratio for them is going to be a 9 to 3 to 3 to 1. So you're going to have roughly 1 that is going to show the homozygous recessive trait, 9 are going to show the homozygous dominant trait, and those 3s in there in the middle are going to be a mix of tall and terminal and short, or yeah, short and axial. If you don't believe me, you can work out the cross and try it out yourself. But that is pretty much how it always works out. Number 10 here. Suppose a white, straight, what the heck is going on? Okay. Suppose a white straight-haired guinea pig mates with a brown curly-haired animal. All 5 babies in their first litter have brown fur, but 3 are curly and 2 have straight hair. The second litter consists of 6 more brown offspring, but 2 are curly and 4 are straight. Assuming curly is dominant to straight, what are the genotypes of the parents of the offspring? So the parents are the ones who had the litter. We didn't change the mom and the dad at all throughout this entire cross. They had more than one litter. Now we're looking at, let's see, straight is going to be a recessive trait. So we have a white straight-haired guinea pig mating with a brown curly-haired guinea pig. And as we're looking at those babies, they are all brown. So that means that the brown one was probably 2 capital B's for brown. And the white one would have been 2 lowercase b's. Because if there was a capital B lowercase b, odds are we would have had at least one white-haired baby somewhere in one of those 2 litters, but we did not. Now, with them having both curly and straight hair, we know that those are just odds as to what you could have or not have. But since both of them were shown, we know that straight hair is going to be a recessive trait. So I'm going to go with 2 lowercase r's. Let me write that a little bit better so you can see it. And since we did have both, we're going to have a heterozygous over here. So that's going to be our parents. The offspring then are all going to be heterozygous for brown. And they could either have curly hair or straight hair. So they would have either been heterozygous for the hair, or they would have been capital B, heterozygous for browns, heterozygous, and lowercase for the straight hair. Those are 2 options. What is the probability of getting 2 female guinea pigs with straight hair in a row? So we're just talking about the color of their, or not the color, we're just talking about the texture of their hair, so we don't have to worry about the brown coloring at all. So you could set up a little tiny Punnett square. You have to make it a little bit bigger somewhere else. And I'm just going to put in the hair type. So I know that mom's, and I'm just saying that it's mom's, I don't actually know it's another, but mom was homozygous recessive, and we'll say dad had the heterozygous genotype. So the probability of getting 2 female guinea pigs with straight hair, you would have a 50% chance of it coming out straight, and a 50% chance of it being a girl because it is a male. Okay, let's look at one more, and then you guys will do number 12 on your own, which has 3 parts to it. About 70% of Americans get a bitter taste from a substance called PTC. It is tasteless to the rest. The taster allele is dominant to non-taster. Also, normal skin pigmentation is dominant to albino. A normally pigmented woman who is taste blind for PTC has an albino taster father. She marries an albino man who is a taster, though the man's mother is a non-taster. Show the expected offspring of this couple. There's a lot going on in that particular Punnett square. So first, I guess we'll go with the pigmented skin. So a normal skin pigmentation is dominant. A normally pigmented woman. So normal is dominant to albino. So I know she has at least one capital N. Now it tells us that her dad is albino, so that means that she would have gotten a recessive allele from him. So she's heterozygous for skin color. She's marrying an albino man. So he's going to have two lowercase alleles. And she is taste blind, meaning that she cannot taste it. Now, the tasting allele is dominant to non-tasting. So in order for her to be a non-taster, she would have to be recessive then for that trait. Now, the guy is a taster, so he has a capital T, but the man's mother is a non-taster, so she would have had to be homozygous recessive in order to not taste it. So show the expected offspring of this couple. You could go through, you could do a big dihybrid cross, or you could shrink it down a little bit and do two monohybrids. I'm going to do the two monohybrids. So, as far as skin pigmentation goes, they have a 50% chance of having a normal skin pigmentation. 50% albino. And then when it comes to tasting, it's a 50-50 as well. All right, so that's about it. I'm going to have you guys do number 12 on your own. Just so you know what you're looking for, it says in pigeons, the checkered pattern is caused by a dominant allele. A plain, non-checkered pattern is recessive. Red color is also caused by a dominant allele. Brown is caused by a recessive allele. So you're showing an expected offspring of a cross between a homozygous checkered red bird and a plain brown one. So you're going to do this first cross here and carry this cross through the F2 generation. So you're expecting to get what? Heterozygous children for all of them. And then you're going to go into the F2 generation, pretend that chickens can do self-crossing here, and see what you would get in your F2. Carry out to the F2 generation a cross between a homozygous plain red and its homozygous checkered brown female. So ignoring A, then you're just going to do B on its own with two crosses. And last one is a plain brown female pigeon laid 5 eggs. The young turned out to be 2 plain red, 2 checkered red, and 1 checkered brown. Describe the father pigeon. So you know what mother is already. So knowing her genotype, what would you have to have dad be in order to get those 3 different types of birds? All right, guys, I'll talk to you later.